think there may be still a few people joining us, but for those of you, I don't know where you are. For me, it is good afternoon. For some of you, it may be good morning, and for some, it may even be good evening. But welcome. I see we've got at the moment just over 80 attendees. Quite a larger number gave indication that they would join us, so we'll see them as they come in. But thank you for participating in this IABSE webinar, which is hosted by the South African group of IABSE. And let me just introduce the people you see on the screen, our panelists. My name is Jan Wium. I'll be the moderator for the session this afternoon. With me is my colleague, Professor Roman Lenner. He is the chair of the South African group, and both of us are colleagues at the Stellenbosch University. We are within eyesight of Table Mountain, about 50 kilometers from Cape Town on the southern point of Africa. And then we've got our speaker, Dr. Anna Bauer. I'll introduce her to you a little bit later. But we've also got our support staff at our IABSE headquarters in Zurich. We've got Firat Cicek there and Brenda Rika Bors, and they'll help us with the technology if we get stuck. But let me give some announcements about the arrangements this afternoon. I'm going to start by showing 5 or 6 slides just to introduce IABSE for those of you who are not familiar with the organization. Then we've got a short video of 2 minutes from the sponsor this afternoon. And then I will hand over to our speaker, whom I will also then introduce. So I'm going to start by sharing my screen and showing you a few slides about IABSE. So let me just get to that. I think you should be seeing my screen at the moment. All right, as you can see, IABSE, the International Association for Bridge and Structural Engineering, was created in 1929 already. As you can see, quite a lengthy period of time that we've been in existence. The mission of IABSE has always been to exchange knowledge and advance the practice of structural engineering worldwide in the service of the profession and also the society. The association has about 2,500 members in close to 100 countries. All aspects of structural engineering are addressed. And I think it may be useful to say that while we've got bridges in the name of the association, we cover all structures. So whether it is buildings or bridges or tunnels or whatever it is, structures is what it is all about. We also look at construction processes. As I say there, all aspects of structural engineering are actually addressed, and that starts with planning and design, also construction, operation, monitoring, maintenance, rehabilitation, even down to demolition and dismantling. And while always taking consideration of the economic, environmental, aesthetic, and social aspects. I always find it interesting to see where the membership come from, about half of them being consulting and design professionals, about a third of them involved in education and research, and then about 10% each of construction companies and authorities, owners, and clients. There's quite a large number of activities, and I haven't got space for that in this short presentation of mine. Probably the flagship activity of the organization is our Structural Engineering International Journal, which comes out 4 times a year. But then the organization also publishes structural engineering documents, books, basically once a year that captures one or other typical topic for the year. We've also got conferences, conference proceedings and so on. And every year there's the large conference, more or less in the month of September. This year, the annual congress will be in Ghent, in Belgium, and you see the dates over there. An exciting new addition to the activities of the group, of the association, is the task groups, which now allows people up to 4 members, or even non-members, to get together, identify a topic which they would like to research and produce something. It can be a task for producing a document or a paper or even a seminar, but these are short-term projects. normally consists of 1 or 2 IABSE members, and they can invite others to participate as well. This is exciting because it gives people the opportunity to really contribute from their side. There are different membership possibilities for individuals, universities, companies, and even for students. But with that then, that's my overview of IABSE. I would like to hand back the screen to my colleagues in Zurich to show us the video of the sponsor being Balbec, and we want to thank them for their contribution this afternoon. So Fahad, if you can screen us the video, it's a 2-minute presentation.
Balbec.
Thank you to our sponsor, Balbec, and also to Fahad for screening the video for us. Now that leaves the preliminaries behind us. For those of you who may recently have joined, you just in time for the big show of the afternoon, the real session. And for us, it's a privilege to welcome Dr. Anna Bauer, who's the presenter this afternoon. She's going to talk to us about the parametric structural design with isogeometric analysis. I look forward to that. Anna is a structural engineer with Meyer Ludescher partner. She's got a civil engineering qualification and also a PhD from the Technical University in Munich. And one of her accomplishments was the fact that she was awarded the International Association for Space and Structural and Spatial Structures, Shell and Spatial Structures Hangai Prize for a paper on sliding cables with isogeometric analysis at their annual symposium. But Anna, it's a privilege having you with us. Thank you. We look forward to your presentation. Just before you start, for the new attendees, just a reminder, you will see that there's a question and answer section on your screen. So if you've got questions or answers related to our presentation and even related to IABSE, feel free to post them there. We will address the question and answers after the presentation. If you want to chat amongst yourself, maybe greet your friend who sits on the other side of the world, feel free to do that in the chat, but the panel will not react on the chats. The panel will look at the question and answers. But with that, then, thank you. Over to Dr. Bauer.
Yeah, thank you for the kind introduction. So, and it's a pleasure being here and share my thoughts about my findings of parametric structural design. So now you should see my screen. And yeah, so my name is Anna Bauer. I'm a structural engineer. As already mentioned, I'm currently working for my Ludescher partner in Munich, where I also do some parametric design, but more focused on bridges and the geometry side, so really the design. And before that, I was a PhD student at the Technical University of Munich, at the chair of structural analysis of Professor Bletzinger. And my research was focused on the development of new methods for the isogeometric analysis, and also with a focus on the application on lightweight design. And like a big topic for me was also making it applicable for real engineering offices. So I always had this in mind. And while doing that, I discovered the potentials of parametric design. So today my talk will be about the time at the Technical University of Munich and how to do structural design with isogeometric analysis. And this bridge here in Italy is like a really good example for what we were looking for. So it's a non-standard bridge, but it's somehow complicated. It's not possible to just draw it and then do the calculations. The shape of the support construction is chosen such that it has a good utilization. So it's mainly used by normal forces. So a membrane shape is adapted for this concrete bridge. And as it is not possible to just like draw it and then calculate it, it's really beneficial to have parametric design inside this design chain, because there are so many things that you have to consider and that you are not able to control. So you need the analysis in order to generate your design and also the analysis to evaluate it. And the parametric feature is really good because by that you can control the outcome of your analysis shape and can fast generate like a lot of variations of your design idea. So, and this was the goal during the whole PhD, so to create something where it is possible to try to get this parametric design and being able to generate like not only those standard structural ideas, but also getting it a little bit further and have the creativity to generate new things. And how should it look like in the end? So I have a model or video of this bridge here. So it's all of that is done with Kiwi 3D and in Rhino and Grasshopper. So you can generate your geometry model for the initial surfaces with respect to certain parameters and generate the geometry by that. Then you add some threshold parameters to your geometry in order to be able to do the calculation. The calculation should then automatically run in your CAD program, so you don't go to a separate FE solver, but you get all the FE results there. And yeah, you can see the final result. This result of the form finding is then taken into the second analysis, which is a structural analysis, in order to evaluate the feasibility of the design. So you take again the geometry, which was generated before, add some structural values like loads and supports, do again the calculation, and then get directly the results in your CAD program. And yeah, all of them, so you can visualize deformations, but also stresses and things like that. So this is the final vision, and the way there I want to show you now. So we had this project of Kiwi 3D together. So it was the chair of structural analysis together with Structure from Stuttgart, which is an engineering office. And together we developed the plugin Kiwi 3D, which is one of the major outcomes of my PhD thesis. Just some thoughts on Kiwi. So the basic goal or concept is integrating the isogeometric analysis for structural analysis into a CAD environment. So in our case, this was Rhino and Grasshopper. as said, we had this team, and basically it was me from the chair of structural analysis being responsible for the necessary methodological developments and for the FE solver and the interface, and Philip Langst, who was responsible also for the interface, but also for the application, so testing the applicability of the whole plugin. And we started this project in 2015 or 16, like somewhere then. And we had the first release already in 2017, and now it's fully available to everyone since 2019. Since then, we already run several workshops and got some quite positive feedback about that. But in order to understand the whole process and what's behind it, I want to start my presentation by talking about isogeometric analysis, as is one of the key features of this parametric design tool. So isogeometric analysis was introduced by Tom Hughes in 2005, so it's quite new, or 15 years, it's quite okay. And at the chair of structural analysis, we took up this topic in 2019 with the PhD thesis of Joseph Kindl, who developed like a Kirchhoff-Love shell element for the isogeometric analysis. And the key idea is using the CAD basis functions for the simulation as well. So in the usual design process, we have this, first we identify the problem that we want to solve. We model a solution in CAD, a possible solution. Then we take this to the FE environment by meshing it and transforming the model in a FE suitable model, do our structural analysis, our optimizations, things like that, evaluate the results, and out of that, if it's not sufficient, we redefine our geometric input. And this process is kind of chopped into parts. So we first have the design in the CAD environment, and then we have the engineering part in the FE environment with the separate models. So this is quite, it's not that optimal. So isogeometric analysis has the goal to like only use one model. So we take the CAD model, as it's probably not possible to exchange with this part, and move the structural analysis into the environment of CAD and also use the same model, so that we always stay in the same environment. So we go from this partitioned workflow where we have the loop of the parameters of the geometry and the topology, which is in CAD, and a separated loop with the structural parameters, which can only be combined with additional conversion in between the two models, and go to this unified workflow where we only have like one environment and we have all parameters available at all the time. And Classic FEA has another problem. So we have to do meshing in order to generate our FEM model. And also, if we lose this inaccuracy due to the kinks that evolved by the polygonal measures that we usually use for FEM, we might get some inaccuracies. And if we cut off the connection to CAD, we cannot change our model anymore. So if it's meshed once, it's meshed, and we cannot change it if we don't go back to CAD and redo the meshing thing. So it's there are some disadvantages with that. So in order to avoid that, we go to the CAD and think about how we can do the geometry descriptions. So usually there are several types of geometry descriptions. However, for like daily practical engineering, we cannot find like a mathematical formula for our geometries. It's not suitable for complex shapes. So what we do instead is that we discretize the geometry by points and then compute a curve or surface which is in between the 2 points. And there are two possibilities. So either we are interpolating the whole points, or we are only approximating them. And the approximating technique is the standard in common CAD programs. So first there were these Bezier curves developed, but the common CAD programs now, like the standard, are B-Splines. And how do we describe the geometry there? So we have the points, and they are multiplied with basis functions, which are defined by a polynomial degree and a knot vector. And by that, we get the smooth curves. And why am I talking about that now is because you can understand isogeometric analysis better if you understand the geometry behind isogeometric analysis. Because after the geometry, it's basically the same as classical finite elements. So the difference is gained by exchanging the geometry description. The basis functions are defined in a recursive way. So we first compute the basis functions for polynomial degree 1, and then we increase the polynomial degree until our desired polynomial degree. The B-Spline curve has several advantages for the structural analysis. So we have only a local support. It's also nice for just the design. So if we change one part of the geometry, not the whole geometry is changing, but only like in a local area, which is quite beneficial. And we have some other features like partition of unity, non-negativity of the basis functions, and a linear independence. What you also often hear is NURBS. NURBS is an extension of B-Splines, and they allow all those shapes to present them in an exact way. So parabolas, ellipses, and hyperbolas. And what is done here is that we just extend the B-Spline formulation by additional weight, which is assigned to each control point. And by that, if the weight is high, the curve is pulled towards the point, and if it's really low, like the point is ignored. So we have those different types of curves. NURBS has the most freedom for the design. However, like mostly B-Splines are only used in the CAD programs, but of course they also can handle NURBS. And for surfaces, we can basically do the same. So we just take two NURBS curves or B-Spline curves and put them into a tensor product. So we multiply them over each other. And by that, we can define a curve by two knot vectors, two polynomial degrees, and a control point net. And the same can also be done for the third dimension. So if we add the third dimension here, we have an additional tensor product, and like 3 knot vectors, 3 polynomials, and things like that. However, I must say that this is usually not the case. So you won't find any NURBS solids in classical CAD programs, as they are not working with them. So there will be no control points inside the surface, but only there will be the boundary surfaces depicted. So you only will see them. And so having the geometry ready, we can go to the isogeometric analysis itself. So the definition of the FE elements is a little bit different. So in the classical case, you have this polygonal mesh where you put the degrees of freedom on the nodes, and the element is defined in between. For isogeometric analysis, we somehow do the same, but we put the degrees of freedom onto the control points, which are outside of the surface, so they are not lying on the surface. And the element is defined in between the defined knots. But what they have in common, that for each element, we have like a constant set of nodes and basis functions that are non-zero. So like the treatment of the element is then again the same if we have the basis functions available. And the same thing can be done also for the surface. So then there are two node lines defining the area of the element. And those elements are then integrated by a mapping from the physical space, so the geometry, into the parameter space. So this is the space defined by the nodes. And this space is then again mapped into the Gaussian space, which is actually the space that we can integrate with numerical methods. There we can define some stiffness matrices or element formulations for the structural elements that we need. And there it's basically the same as for classical structural elements. For each element, we define our local stiffness matrix, and then we assemble them in a global stiffness matrix according to the degrees of freedom in the global system. By that, we were able to develop some isogeometric structural elements at the chair. So it started with the Kirchhoff-Love by Joseph Kindl, which was then extended or adapted for the membrane element by Benedict Philipp. And I was working on a 3D nonlinear beam element in order to complete the structural construction elements for everyday analysis. And of course, out of the beam, you can also generate a cable. So the question, is this already enough for a fully parametric CAD-integrated workflow? No, it is not. It is necessary to extend the isogeometric analysis to the isogeometric B-rep analysis. And where is the B-rep coming from? So in CAD, you don't only have these rectangular shapes as they would be naturally from the NURBS surfaces that have just this rectangular shape, or rectangular topology to be correct. But you also have more complex shapes like triangles or structures with holes in the middle, and yeah, what you can see here. And in some cases, this is possible to depict with this rectangular topology. However, this is not practical. So CAD uses another technique to be able to generate the shapes. So it takes the full rectangular shape and then just cuts off or cuts out the parts that should not be visualized. So this technique is called trimming. And then other shapes are assembled from some smaller shapes. So they are coupled together, and this is also part of the B-rep analysis, so the boundary representation. So this is also the origin of the name isogeometric B-rep analysis. And if we go to a real CAD model, here's an oil sump that we received back then. And this CAD model consists of several patches, so it's a multi-patch. So you can see here there are quite a lot. So you need to be able to couple them. And you have the discretization that is just there from the designer. This also consists of trimmed patches, so the actual patches are larger than the visualized surface. And as for classic FEM, it's basically the same. It's for the analysis quality, it's much better if we have somehow equalized mesh. So of course we can do the analysis on the distorted one, but the analysis will be better if we have a better mesh. It's the same principle. And here, isogeometric analysis and NURBS provide another really important feature. So we can do mesh refinement at every step of our analysis. And while refining the geometry model, we are not changing the shape of the geometry. So if we have in the beginning a perfect sphere where only a few control points, which maybe not enough for the analysis, we can just add some control points, so FE nodes and design handles, by two techniques. So this is order elevation, where we increase the degree of the polynomial degree of the geometry, or where we insert just elements into the mesh. By that, we get more control points and more freedom. And this is also really important for the analysis, as only a good mesh can provide good results. So if we only use a few control points, just as for classical finite element analysis, the result is not really good. So here I tested the elastic curve, so where we bend up just a simple beam or a shell strip. And it's possible to depict the flat surface with only a few control points, so even 4 would be enough. So here I tested 10 in order to be able to even bend it up. So this is also one thing in isogeometric analysis, as you can depict like smooth shapes with only a few control points, it's easy to forget that you need to add some degrees of freedom in order to make it possible to deform the shape in the necessary equilibrium state. So here for 5 control points in a row, we already see the result is just not good enough. And even if we apply more, we still need to check if there were already enough points. And as the shape is always smooth, it's harder to predict if it's a good result. But we get a better result if the result is, or the analysis, the mesh was suitable. So it's important to add some degrees of freedom and do the refinement and not forget it. And by that, we can then compute and simulate the structures from the architectural application. So this here was an outcome of a student's workshop at the IABSE. But it can also be used in the industry, in other industrial applications, just like here, where we had a project with automotive industry or other industries here. Colleagues of mine were also researching on the implementation of isogeometric FSI analysis, which was also quite successful. So this example here is from a colleague called Andreas Apostolatos, which also already finished his PhD. And to sum up, why is isogeometric analysis so beneficial for the structural design? We have this continuous smooth basis functions, which are able to refine the analysis or the geometry at every step. So if we are not satisfied enough with the results, we can just add some more degrees of freedom to the curve. So just add more control points without changing the shape, and it's fine. We have this parameter space that links the material points at every stage of the analysis. So we always know, okay, this material point was in the beginning there, and then like after 2 steps, it will be there. So we always have this link that is not destroyed by changing the model and reparametrizing the geometry. We can use recoupling without the matching discretization. I will show that later. And as we have this new CAD-Integrated workflow where we go from CAD, generate the CAE model, so the engineering model, and the results back in CAD. And we can just add this like a module next to each other. So from the results, we can then start another analysis and using the same model. So isogeometric analysis is really good for structural design. And because of that, we now can think of the next point, how to make it possible to have this CAD-integrated structural analysis. And furthermore, we will also want to add this parametric feature, which is already available in many CAD programs. And which is already very beneficial to the design of the geometry and shape, but it also can be enabled for the structural analysis. And isogeometric analysis is also really good for the parametric features, as we have this possibility of the direct CAD integration, as we are not changing the model. So we don't need this meshing in between the geometry generation and the FE analysis, so the structural analysis. And we have this independence of parametrization. So we don't have to think about our structural model when we are designing the geometry. So we can just design it and generate the structural model later. And where is this important? Like a simple example for this is this surface that should be coupled to a beam, which should be somehow in the middle. With NURBS, I can just model it and have to ensure that the geometries are matching. But as I do it with CAD, they will match in the tolerances that I apply. If I would have to measure it for classical finite element analysis, I already would have to think about this coupling in between the surface and the curve when I generate my mesh. So there, it's not possible to just generate the mesh for the curve, so the polygon for the curve and the surface separately or independently, but I have already to know, okay, they have to work together and they have to share the nodes in order to be able to couple them. Isogeometric analysis, there I can just use weak coupling with matching, without matching discretization, but with matching geometry. So how the workflow looks like, you already saw it before in the video a little bit. So in the first part, like always, we have the pre-processing. So we generate our geometry model where we throw the curves, surfaces, points, topology, and things like that. Then we generate the analysis model by defining what type of analysis we want to do, which kind of elements we need, the materials, cross-sections, and things like that. And of course, also the boundary conditions, so supports and loads. Having pre-processed all of that, we can hand over the data to the FE solver, to the IGA solver, that then does all the things that are related to the integration and stiffness matrices and force vectors and solving the final structural analysis model. After the solving, we can load this back into the post-processing. And there we have then the deformed geometry and the results of the analysis. And here we never change the model. So we have this continuous workflow. So it's always the same NURBS model. And that is true, can be shown here. So here you can see deformed models that are used, were computed with Kiwi. And what you can see here is the deformation process of the two shapes, but also the control points of the NURBS geometry. So during the analysis, there's no backmapping or something. It's just always the NURBS curves that are used for the computation of the structural behavior. And this feature is really nice for applications, for example, like this. So in the beginning, I looked for some application cases, and the One Ocean Thematic Pavilion and was one of the things or the structures where I thought IGA could be really beneficial, as we have this bending active louvers for the facade. So the facade can open up by bending or pushing the ends of the louvers towards each other. And by that, this opening of the facade is created. And analyzing this in the CAD environment is really nice because, for example, we have like at the same time the data of the structural analysis available. So is it even possible to bend the louvers in that way? But we also have some other features, like we can evaluate the opening states. Is the light incidence okay for the interior design and things like that? So we have like several information in one environment available at the same time, and being able to adapt the model due to several different analysis aspects. So here is really nice. And another application could have been the King Fahad National Library, where the facade is also, the facade is a membrane structure. So it consists of several modules that also can be defined by some parameters. So by the width and the height of the module, and also some structural parameters that are important for the shape as well. So the pre-stressing of the edge cables and the membrane itself. And both of them need to be considered simultaneously in order to do this parametric study. So once the pre-stress relation is changed, and once the relation between the width and the height, and by that we get again different appearances of the whole building, and also like the building physics are influenced by that as well. And by that we can somehow set up a model that is able to evaluate several aspects of the whole structural design process, not only focusing on the if the material is good enough to withstand the loads and influences from the outside. And having this smooth parametric setup, we can integrate this into an optimization loop. So if we know what we want to look at, we can evaluate a model and generate a parameter update out of it. And this parameter update is not necessarily only the geometry, but can also go into the analysis model. And an example is shown here. So the design idea is to get this bent beam. So it's a bent beam from a flat lamella, and then the stiffness should be manipulated in such a way that there are several other lamellas are added in between somewhere in order to generate exactly this shape here. So if you just do it like that, the equilibrium state would be in another position. So, but if I run the optimization, I can find a configuration that is almost in the same shape as I defined in the initial thing. And as we have the smooth loop, we can not only use it to do one analysis, but as I already shown before, I can use it for like combining two analyses together. So here's this first construction stage. So it's like the classic thing, geometry and simple examples. So we have this two-story frame here. So here is only the first frame in the first analysis. We generate the analysis model by loads and supports, generate the finite element model with integration points and things like that, and get the result in cut back again. And this result we can then map to the second analysis. So we then can define the geometry with respect to the deformation of the first part, which is crucial to consider if the deformations are not really, really small. So as you can see here, the column of the second frame has to be a little bit longer in order to be able to have a horizontal frame at the top. And again, we can also link the analysis model to the first model by telling the lower part of the deformed geometry, okay, you've been initially straight like in the beginning here before. By that, we can also transfer the information that this is not like the first step, but the second step in the analysis tool chain. Having that, just generate the FE model again, and we get the final result of this two-story frame. And of course, we can also add parameters to this analysis, so height, width, Young's modulus, and cross-section and things like that. And the nice thing now is that if we change one parameter, for example, the Young's modulus of the lower column, like the whole tool chain, all the analysis can adapt to this change. So in the end, we get a result that considers the initial change. So this can be used, for example, it could be used for the ITKE research pavilion, which was designed in 2010, where they had this initial straight lamellas that then were consecutively bent towards, next to the existing structure. So during each step, the pavilion deforms a little bit, but this technique can also be used to connect different kinds of analysis. So, for example, you can be used in the design cycle of membrane structures. So we can connect form finding analysis, structural analysis, and also manufacturing analysis. So in this case, cutting pattern. And an example for this is this parametric design of a beach board. It also has some elastic members, so it's also bending active, so even maybe a level higher. And the design of this could be that we start with the flat geometry. So we have this initial straight beams, and we know the base area of our beach board. So we bend, and then we attach some structural values to the geometry. We bend them into shape and use this for defining the connection points, bend them up. The result is then used to generate the shape of the initial membrane. So here it's really nice to have it in CAD, because we can just use normal CAD features to generate this initial surface. And we can also have the starting point everywhere. So M1, M2 are not restricted to nodes of our previous FE analysis, as it maybe would be the case for classical finite analysis. Then we also assign pre-stresses in cable and the membranes and get the final result, which is our design goal. This design can then be further evaluated, for example, by the manufacturing, so generating the cutting pattern, or we can also take the geometry and put some wind loads on it. So these were some potential applications which I personally worked on during my PhD thesis, but there were also some real-world projects. So there are only some of them, and today I want to show you two selected cases where Kiwi was used. Kiwi and isogeometric analysis was used directly in the design phase of the structure. So the first one was the Isogeometric Pavilion. So it's the Danish pavilion at the Biennale in 2018. The design or the whole structure was developed by CETA in Copenhagen, but structure was part in the form finding and structural design and detailed planning of the whole pavilion. So we had a part of it in the whole design phase. And the final pavilion looked like that. So it's textile with some actively bended rods. And the design phase was done like that. So there were several tools used, but Kiwi was one of them. So, and Kiwi could be used as an intermediate step in between like fast design explorations and really accurate and detailed design evaluations using all the design codes, and this was sophisticated. But Kiwi had the feature that was more exact than the fast design exploration tools, but still like in this parametric environment where it was possible to somehow faster evaluate if the structural design is feasible or not, and if it's worth it to put it into like a total structural analysis. So in this project, Kiwi was used in this part, or in this phase here with this work. And the whole pavilion consists of several modules. So CETA developed different types of modules that could be used, and they were then assembled to this total pavilion here. And what we could do with Kiwi was that we simulated this bending process of the modules. So first there were these straight rods that were then bent by a cable into this bent shape. A membrane was inserted and form found, and then the cones were pulled out, and in the end there were some wind loads on it. And the whole calculation is done in one consecutive grasshopper script. So each part is marked here until like the structural analysis with the wind loads, and the shape generation looked like this. So it's bending down, and the membrane is added for the form finding, and the cones are pulled out. And here on the wind loads, they were put on the structure. And in this case, Kiwi worked quite nicely. And the second example, which I want to show, is a bending active one. It's a canopy at the Hotel Intergroup near Ingolstadt. The design was, so the whole structural idea is an asymptotic grid shell, which was developed by Eike Schling also at TUM. And for this pavilion, also Jonas Shikore was part of it in developing the whole structural shape, and actually was leader of this part. And I was part of this project as a consultant for using isogeometric analysis for this complex design process of this shape. So the whole canopy consists of four modules of this type here. So we have a stiff edge beam and some initially straight lamellas that are bent in this 3D shape and then stiffened by the edge beams. On top of it, there is also a membrane. And the whole process is done like that. So we have this this flat grid that was assembled by the flat lamellas. And this flat grid is then pulled into shape by, in this case, a crane. And after the pulling in shape, the stiffness are added. And Kiwi and the parametric design could be used in order to find, first of all, this assembly of the flat grid, how to find the energy minimum in order to put the minimum amount of force into it in order to get the shape, but also to evaluate if is it even possible to twist those lamellas into the shape. So getting the evaluation, if it's even possible to have this final shape, or will the material crack, and also to optimize this mounting process in order to find the optimal points where the structure should be pulled up into the shape in order to put the minimum amount of energy into it, so not having to press and pull on the sides in order to get the final shape. So this here is this mounting process, and by that we could generate this fantastic structure, and was really glad that I was part of this process. And this will be also the end of my talk. Looking forward to your questions.
Well, Anna, thank you very much. Impressive procedures and really impressive structures that can be designed with this approach. So thank you very much for this exposure and bringing this to us. I noticed one question there, but I want to invite our attendees to post other questions, more questions in the question and answer section, you're welcome to do so. So remember, we're not posting the questions in the chat, but put them in a Q&A slot that you see on your screen. But there was a question, Anna, about the use of isogeometric analysis for, say, masonry structures. Would that be possible? Is it already possible? Question that I've got here.
Yeah, there's actually a research project going on at the Chair of Structural Analysis by a colleague, Tobias Teschemacher, who works on that and hopefully has soon some good results that he can show the public. So it's basically the same. So you can use, can split up into points and then use this as a background mesh, or even, yeah, okay. It's possible.
Can you see the second question there that that talks about potentially calculating the pre-stress for the cable-stayed bridge cables? And you maybe let me read it while you think about the answer so the audience can hear that. Question is, well, this method will potentially allow calculating the pre-stress for the cable-stayed bridge cables, taking into account stage construction. We tell the program what results we want to arrive at, and it can calculate the pre-stress for the added cables. Is that possible?
At the current stage, it's not directly possible. However, you could integrate this optimization loop. So if you know where the structure should be in the end, you can just compare the deformed structure and the final structure and update the cable stresses depending on the difference of the structure, and then just choose the value which is closest to the initial design. But it would also be possible to just directly integrate it into the analysis, but that's not yet done. So.
Okay, thank you for that. Another question here from Paul Shepard. What advice would you give to an experienced finite element user who is thinking of swapping Karamba to Kiwi 3D?
I mean, it's somehow similar, of course, but it's pretty understanding how NURBS geometry works that makes a difference. So it's actually the difference is only in the geometry, and currently I must also admit Karamba is maybe a little bit faster, but still we have with Kiwi we can have this whole design change, so we can have this loop of design iterations and manipulate in between the analysis, the geometry again. So, and for the application, it's mainly about understanding how NURBS geometry works, and that's the whole difference, actually.
So, sorry for stepping in. Are you trying to say that it's if the geometry is very complex and curved, then you would recommend Kiwi versus Karamba? If you're looking at shells and membranes and stuff like that.
Yeah. So if you have a smooth shape, it's definitely better to use NURBS for the analysis, because then you can directly compute on them, and you also have the results as a NURBS surface. So that's also a big benefit, so that not only like the step from the geometry to the analysis is easy, but also if you want to further use your result for something else, that then this is not a meshed model, but like a nice NURBS surface.
Can I just ask one more thing, please? I was just interested. Right. The amount of control points, when you said if you're satisfied enough, how do you judge that you're satisfied enough?
So it's experience, actually. Okay. just like for classic finite elements. But you could also do the same thing what you do for classic finite elements. You increase the refinement, and if the analysis doesn't change, it's good.
Yeah.
But so a lot of that can be done just by experience, actually.
Thanks.
Okay, I see there's a question about conventional structures. I also want to ask that one, but let's just wait with that one for a moment. There's another one which says, can you say a few words about if, for example, we want to add moment boundary conditions for your isogeometric analysis, especially if you have some control points outside the boundary surface?
Yes, it's possible to add some moment boundary conditions. However, it's not that simple as for conventional finite elements, because it's outside, so we need to apply them weakly, meaning that we have to define a criterion that puts this onto the shape, and then from the shape we again put the resulting forces onto the FE nodes. So there is a step in between. We cannot just put like a rotational constraint or a moment constraint directly on the node, but we have to calculate the resulting forces for all of the nodes that influence this point on the surface in order to be able to add this boundary condition that is rotating or a moment, things like that.
Okay.
But it's possible.
Thank you. I was also wondering, and it ties in with this question that I see here about conventional structures. So I can certainly see the benefit of using Kiwi 3D for spatial structures or shell structures, but would that also be applicable to conventional structures, say a building that's got columns and slabs?
Yes, of course. I mean, the difference is maybe not that big anymore, but still you're inside the CAD environment all the time, and this non-matching parametrization is really good because you can just move around your columns without changing the parametrization of your slab, for example. So you don't have the node on top of the column in order to couple the column to the slab and things like that. So you're still really flexible. And if you want to like evaluate like a lot of varieties of the same structure, it's good. The advantage for like doing one analysis is maybe quite small, because for the classic structures, it's usually also quite okay to do the meshing for the analysis. So there was a lot of work done that this workflow is smooth, but still you have this flexibility of modifying your system. So you can modify geometry parameters and structural parameters at the same time and get the result directly and see how is this affecting my system. So still there's a huge benefit from the parametric design, and the parametric design benefits again from isogeometric analysis.
Okay, thank you. I see another question there about timber structures. Well, we'll get to that. The question here that I understand very little of, but you'll obviously be able to handle this one. I see the last one, you mentioned optimization loop. Which kind of algorithm have you used, gradient or genetic? And have you performed the optimization in Grasshopper as well? If yes, which node have you used?
Yeah, so this was actually quite simple optimization. So I used the genetic algorithm, so the Galapagos component, which is native for Grasshopper. So it's quite easy. So you just set up the analysis, and then the design criteria was that the distance for several points to the intended design shape was small, or is minimized, and that was then just inputted into the Galapagos optimizer. For a master's thesis, we already had like gradient solvers implemented into the Grasshopper environment, but this is not was not published. So, but it's also possible to connect this to any optimizer. Actually, if it's inside Grasshopper, you can use it, and if you know how to evaluate your results and create the update from it.
Okay, I see another question about whether it can be used for timber. I would assume it's applicable to any material, so it's not material related.
Yes, it is. So it's the only thing is that currently in the release version of Kiwi, there is only isotropic linear elastic material. But like underneath, so in the solver, there are already some more materials implemented and you could use it, and it's definitely, so you can definitely use it with isogeometric analysis. However, you maybe for some features, you have to still define the projects. But for like this classic timber structures where we only have linear elastic behavior, it's working. I already used it. So.
Okay, if I say to you, I think people who would be very excited about this method would be architects, because they are basically now doing away with engineers. The architect can just say, okay, I draw my thing in CAD and press a button and it'll analyze.
Yeah.
What's your response to that?
Yeah, it's not that easy. So I still have to have the knowledge about how structural analysis works. So what are the important things? What do I have to have in mind? So of course, architects can use it and also use it for generating those shapes. If it's only about the shapes, I mean, you can do whatever you want. But then for the structural safety and things like that, you still need this engineering knowledge. However, I also think that this like merging the two environments together into one enables the understanding of each side a little bit better, because you get closer to the other field, and this maybe also makes the communication between the two professions better in the end.
Yeah, I think what makes it easy for engineers to become architects, not the other way around.
Yeah, but I like Anna's comment that it actually brings the two disciplines closer together. It creates an opportunity for better collaboration and discussion.
Yeah, because then, like what I see now, like the engineers are always a little bit annoyed if the architect again has some changes in like the column size here, or moves the column like 10 centimeters next to the existing column, and by that, like facilitating this movement between the geometry model and the structural model, it's like better to react to the other side.
Yeah, I was very impressed with Grasshopper and how easily you can change your model with 3 to 4 clicks, and you have a completely different shape. And then if you can, like you say, analyze it immediately, that's a huge benefit.
Yeah. There are two questions that you can do simultaneously. It's the question about whether Kiwi 3D can already do dynamic analysis, such as seismic analyses, and then application of wind and seismic loads. Do you need to do that manually, or do you need to? Can that be done by Kiwi 3D?
So there is no dynamic analysis available yet. And also this, what I showed with the FSI simulations, there is still a lot of manual work necessary. You can only generate the structural model with this plugin. So, and then all like the fluid mesh still has to be done with a conventional approach, or with an embedded approach, which is also a research topic at the chair of structural analysis. Okay. So it's on the way, but not yet there.
You've obviously used this now quite a bit, and you've got excellent experience in that. If somebody now starts, he acquires Kiwi 3D and starts using it, what would be your advice? What to look out for? What are the risks, and what must such a person be careful of?
I mean, there are those things that are risky for all FE solvers. So, I mean, you have to check your model. Did I really model what I intended to model? Things like that. And then there are some specific things like what I shortly mentioned, that with isogeometry, so with NURBS, I can model a smooth shape easily with a few control points, and it's really easy to forget to add some additional degrees of freedom to the structure, because it already looks nice. And if you're used to this kinky shapes, in order to use this as a quality evaluation, this is not there anymore. So you always have to think about, is my NURBS structure or my NURBS geometry even able to depict the equilibrium state? So you somehow have to have an idea how the deformation should look like, or the results would look like, because if it's not possible to depict it with the model, you will not get it in the analysis.
Okay, I see a question asking about non-linear analysis available yet. I would think not yet.
No, I mean, that's the key feature.
Okay, I mean, oh yeah, because you've adapted all the time. Okay, for that.
Yeah, so we have, like for my case, as I was dealing with this development of the beams and things like that, and one of the key focuses was bending active structures, where you have those large deformations from the bending and then from the assembly. So non-linear analysis in the geometric sense is fully available. What is not available is non-linear material.
Yeah. Okay. Roman, have you got any other comments, questions?
No, not really. I was really just quite impressed about what the structures, how could they look like, and that, as you say, if everything's in one environment, that's quite excellent.
Yeah, maybe a last question before we wrap up. At the undergraduate level, should we start thinking of bringing this concept to the attention of students?
Yes.
Yes.
Of course. No, but what I think is like even more important is making the students play with the structures. So providing them an easy possibility to just play around and get this structural feeling, because in the end, this is everything about structural engineering, like to know how the structure will react or have an idea what is going on. Because if you don't have this idea of how it should look like, you never have the possibility to like validate your structural models or your analysis. So it's maybe not about this method, but giving them an easy possibility to like play around with the structures. And then of course it's also nice to get an understanding of how FE works and how it could work differently with different types of FE analysis as well. Yeah, but I think the most important thing is this structural idea of everything.
Yeah, I think understanding the behavior of structure, that's fantastic. So if you can, if this can help to give people a better understanding of things, I think that's fantastic.
But it's very difficult to teach, but we must be doing a better job at it.
Yeah, and there is like really important to motivate them to do it on their own and giving them an easy tool that is somehow playful and makes fun.
Yeah, but it's a great point, because if we talk about, let's say, conceptual design, that's your first stage. Without good understanding of the structural behavior, you won't be able to put together a good concept, or the concept's not going to be great. So that's a very important point, I think.
Yeah. Question about CPU time. How fast does the software run?
Yeah, this is one of the things we still have to work on. It's not that fast. But I mean, you can get, so it's always like a leveling off. You need less degrees of freedom. So the systems are usually smaller than classic system. However, this is more intensive for the computation of each element. And so it's depending on the structure. So if it's like a large structure which is smooth, but then it can be fast. If it's like, I don't know, where you only need some distinguished classical elements, it cannot compare to the conventional approach. But it's, yeah.
Okay.
It's not as fast as other programs, but it's still usable.
Yeah, just a comment that I see here is that someone mentions the possibility of doing some parametric studies, or changing parameters to see the sensitivity of the analysis if you wish to verify your answers. I think that's also quite a valid comment. Someone asks if you would share your contact details. I think what I'm going to answer is, if you want to get hold of Anna, send an email to IABSE headquarters. If you don't have it now, find it on the web, and I'm sure they'll put you in contact with Anna.
Mm-hmm.
I think we need to wrap it up. We've been going for quite some time now. So Anna, thank you very much. Most enlightening, and I think a very interesting presentation. Excellent work done. Congratulations.
Thank you. It was a pleasure.
If you were now locally in Stellenbosch, close to Cape Town, we would have taken you for a nice lunch at a wine farm, but that will have to wait for another time. But thank you very much. And to all the attendees, thank you for your attention. Some of you for which it's already late at night. Enjoy your weekend. Thanks again to our sponsor, Walbeck, and Roman for arranging the seminar. Thank you very much. And then to our staff at headquarters, Brenda and Fahad, thanks for setting the technology up. But Anna, if we could give a hand clap now, we would have given a big applause. But thank you very much.
Thank you.
Thank you all.
Roman, any last words from you before we sign off?
No last words, just again, my thank you to Anna, because I was looking for some activity for our national group, the South Africa national group. And when I came across her research, I thought it'd be quite interesting to share, not only locally, but then through this webinar, and just, yeah, in the spirit of IABSE, share the knowledge. So thank you.
Excellent. And there's another seminar, the 30th of April. What's the date?
Yes, I believe that's the 30th of April. We'll be talking about UHPC structures.
Okay. All right. With that then, thank you. And I think we'll sign off from here. Thank you very much.
Thank you all. Bye-bye.
Thank you.